to conclude the analytic properties. And so this picture here of taking an integral of a certain modular form and obtaining an L function and the nice properties thereof is sort of the motivating kernel behind the Relative Langlands program. So just to sort of move towards other examples, this picture here completes the setting of so-called abelian L functions, where Hecke used this same technique to prove the analytic continuation and functional equation for his what we call Hecke L functions. So where chi here is some character, Hecke character associated to a number field F. Concretely, Hecke generalizes Riemann's approach by writing down some sort of theta series built, maybe it's a multivariate one, where n here in the integrand is maybe the degree of f over q. And by using the modularity of this theta series and some relatively delicate analysis with the arithmetic properties of the number field, he's able to obtain this expression and prove the properties of these Dirichlet series. So moving in the direction of automorphic forms, if we rephrase this in the adelic perspective, then chi will give us a character of the Adel class group, or sorry, the Adel group, which I've called chi tilde here. And we can think of this as an automorphic function on the multiplicative group. And so that's kind of the picture here. We're using these automorphic forms to study the analytic properties of these automorphic L functions. And so a natural question here is, how does this relationship generalize to other automorphic L functions? And so now is the obligatory reminder of what an automorphic L function is. I know that this has come up several times in the last trimester, so I'll try to be brief. So I'll let G be a reductive group over Q. I'll just try and work with Q for simplicity over throughout the talk. And I'll let AG be the set of isomorphism classes of irreducible automorphic representations of G. By the way, I don't want to assume things that maybe should be explained a little bit further, depending on people in the audience. So if there are any questions, please feel free to stop me at any point. Okay, so the basic dream of the Langlands program is to be able to parameterize this set of automorphic representations via so-called admissible homomorphisms. So here I'm going to ignore what the word admissible means. And my morphism here I'll call psi of pi from the so-called this conjectural extension of the Galois group, so the conjectural Langlands group, to what we call the L group of G. So where here G check is the Langlands dual group, and there's a natural action of the Galois group of Q on that group, and so we take the semi-direct product. So this is a dream. I mean, L is not even known to exist, but this is sort of the hope, generalizing the idea of parameterizing via Galois representations. And if you have such a picture, then you can define an automorphic L function for any finite dimensional representation of this L group, just by this L group has natural maps from the Galois groups of the various localizations, and so you could take a Frobenius element at all but finitely many places, look at the image in this dual group, and then let that act on this representation via rho. And so we take there's supposed to be a determinant factor here. Sorry, that's a typo. This is a polynomial, not vector valued. Okay, so we have this Euler product, and this is something that Langlands writes down in this generality, and we think of these as the so-called automorphic L functions. So for the purposes of this talk, I should give a few health warnings. We're going to pretend for simplicity that this dream is realizable. So we have access to Langlands parameters. This is very far from the truth, but in most practical cases, concrete, correct statements can be made. For example, it's not even necessary to use this formalism to define the L functions on the previous slide. If I have an automorphic representation pi, well, if it's unramified at a place V, then this element frob V of psi of pi that on the previous slide, this is just the Satake parameter of the local representation. This is some unramified representation, pi V, and so it has a well-defined Satake parameter, and that's all we need. But the point is that the relative Langlands conjectures, as I will state them, are somehow most from my point of view, they're best viewed as being dependent on the Langlands conjectures. So we would like to say things that sort of extend this correspondence from the previous slide. So it's best to just frame things in terms of the conjectures. And as I kind of alluded to earlier, this can be made precise in a lot of cases where you're really working almost everywhere locally, and the local Langlands correspondence is available in a lot of cases. So it's a health warning, but it's not that bad. Okay, so from that point of view, I'll just use the notation that to an automorphic representation, I have some parameter. And also, just for simplicity, I'm going to assume that the group G is split, so that the actual action of I'm going to kind of equate the L group with the dual group. Apologies if that causes any confusion. Okay, so enough for the health warnings. So let's look at some examples of these integrals of automorphic forms and their relationships to L functions in the classical setting of GL2. So this is, I think both of these examples have come up in prior talks in this series. So the first is Hecke's integral, which generalizes the previous case going back to Riemann. So we've seen several times throughout this series that to certain nice automorphic representations on GL2, one can associate a classical holomorphic modular form on the complex upper half plane. And so I've written down the Fourier expansion of such a form. And if we recreate or sort of reapply the same integral from the previous, from Riemann in this setting, namely take this modular form and integrate up this imaginary axis here, then that's precisely Hecke's integral representation for the so-called standard L function. So here I've used the notation standard to try and align with this automorphic L function notation here. Okay, so in the context of holomorphic modular forms, especially in the relationship to the arithmetic properties of elliptic curves, so when this is a weight 2 modular form, then this integral is important to study the special value at s equals to 1, which has relationship to the classical algebrao-geometric notion of periods via work of Manin and Drinfeld. So that's the one use of the term periods in the context of algebraic geometry. So we're going to talk about automorphic periods in a second. Okay, so this is the standard L function, but I also want to give an example which has a very different flavor in this GL2 setting, which also is connected to some previous talks in this workshop, namely considering CM or Heegner points on a modular curve. So I'll let D be a negative and square free integer, and I realize now that that negative should be the word positive. That's a typo. No, sorry, this is negative. The typo will come later. There's a sign error somewhere. And so we're going to consider, there is a typo. Yes. So for such a D and for a pair, a set of co-prime integers A, B, and C, there exists a unique point in the complex upper half plane Z satisfying this cubic equation for all triples of integers A, B, and C satisfying this discriminant condition. Sorry, this entire line is riddled with typos. So the corresponding points, so these give us these arithmetically interesting points in the upper half plane, and the corresponding points in the modular curve, the quotient by SL2Z, are examples of Heegner points associated to imaginary quadratic extensions. So that here, this minus sign should not be here. And so this shows up in previous talks, recent talks, in discussion of Gross and Zagier and the relationship between Heegner points and the non-vanishing of a derivative of a certain L function. But there's also the case where the L function is not vanishing at the central point, and that is the content of a theorem of Walsh-Bourget, where instead of looking at a derivative of an L function, we get a special value. So I've stated a particular case of Walsh-Bourget's formula just for simplicity. So if my automorphic representation pi is associated to a Moss form of, say, weight 0, call it F, then if I average the this Moss form over these Heegner points, the absolute value squared is this special value of a distinct L function. So it's a product of L functions, which we think of as the standard L function of the so-called base change of pi to this imaginary quadratic extension. And so we see here something going on where now there's either it's a product of L functions or it's related to a functoriality, a functorial lift of the representation pi to this base change. And this formula and its generalizations play a crucial role in dealing with the rank 0 case of the Birch-Swinnerton-Dyer conjecture, whereas the Gross-Zagier formula plays a role in the rank 1 case. Okay, so we've seen two examples of formulas looking at special values or integrals of modular forms. And the point is that these are both classical manifestations of what we call automorphic periods. Both of these settings generalize to higher rank groups with different flavors. The Hecke integral generalizes to the notion of the Rankin-Selberg integral. And Walsh-Bourget's formula generalizes to the so-called unitary Gann-Gross-Prasad conjectures. And the study of the interrelationship between these is an incredibly active and important set of body of work. But one of the reasons why I want to highlight these is that when we re-express these two formulas, a priori very different looking objects, this integral over the imaginary axis and this sum over these discrete points, if we express this in terms of automorphic forms on GL2, they end up being very similar to each other. Okay, so let me go ahead and do that. So let's say what I mean by an automorphic period for the purposes of this talk. So I'll let pi, now I'll let G be my reductive group. I'll let pi be a cuspidal automorphic representation. And I'll take H to be a closed subgroup of G and define the so-called H period, where what I do is I take my automorphic function, I pull it back to the subgroup H, and I pair it against some automorphic function. I've used the word small here because typically this is either trivial, could be a character, or it could be maybe a theta series. All of these things happen. But what we do is we take this pairing, we pull it back to H, and then we integrate over the quotient. I'll always either assume it's a character or trivial for simplicity. But anyway, these are the sort of integrals that we are interested in. And we call such integrals automorphic periods. And so this content of the relative, or the maybe initial goals of the relative Langlands program is to understand the properties of these period integrals. They show up in a vast array of applications, and we would like to have a more systematic understanding of these periods. So in particular, we could ask questions like characterizing the subset of AG where the period is non-vanishing. And once we have that, we would also like to understand the actual values that you obtain. So the relationship between these periods and the arithmetic invariance of pi. So these could be L functions, special values of L functions, or maybe relationships with functoriality. And the field tends to have two aspects that I'll try to explain in the next slide. Namely the global aspects, which are often more arithmetic, and the local theory, where I've written here the tensor product decomposition of my representation. So local theory will be interested in local invariance of these representations pi v, and that tends to have a more harmonic analytic and representation theoretic flavor. So returning to the Hecke and Walsh-Burget periods, I want to see how I can express these things as these automorphic periods. And so the Hecke period involves integrating over the split torus that I've written down here, the diagonal torus of GL2. If one were to, it's a simple exercise to see that if you act on the complex upper half plane via this group, then you're at the point I, you just scale out the imaginary axis. Whereas for the Heegner points and Walsh-Burget's period, we're interested in the period associated to this non-split torus, where again I've made the mistake of putting a negative sign because I assumed that my discriminant d was negative. So framed in the adelic language with respect to these groups, then the two integrals, the integral of Hecke becomes the automorphic period over A, and this sum over Heegner points for Walsh-Burget is nothing but the automorphic period over T. And in this language, the formulas take the following form, namely that, so now in the adelic language, we're normalizing so that the special value is at a half rather than 1. The Hecke period says that the automorphic period over A is this special value of this standard L function times a product of local contributions. And similarly, Walsh-Burget's period, well, okay, we're not looking, Walsh-Burget didn't just have the period, he had this absolute value square. And so that is equal to this, now it's going to be a ratio of L functions. So here, these are supposed to represent the two L functions that we saw previously, the standard L function and the standard L function for the base change. And now we have this new factor, the automorphic L function associated to the adjoint representation. So that's what naturally comes out when appropriately formulated. But again, we have this local factor for each place. And so these are what are often referred to as local periods. These are invariant forms. Here we have an AV invariant form on my local representation pi v. Whereas in this case, since there's this since there's this squaring, we end up looking at these bi-invariant forms. So this is two variables. And so the point here is that the study, in both cases, you see something that looks like it breaks the problem into a global and a local problem. Namely, this period is non-vanishing precisely when the two terms, namely all the local factors are non-vanishing, and you have this non-vanishing of this L value. And likewise here. In the first case, this is actually not, there's actually no local problem. These local factors are always non-zero for some input phi v. And so there is no local constraint, and we get an equivalence. Non-vanishing of the period is non-vanishing of the central L value. Whereas in Walsh-Burget's case, something more subtle happens. These local factors are not always non-zero, and there's some interesting arithmetic invariants that need to be brought into the picture. Namely, there's some epsilon factors which govern when these things are non-vanishing, and that goes back to work of Tunnell and Saito. But one thing that I just wanted to illustrate here is that when framed in the adelic language, these two formulas, which are very different in the classical setting, take on a very similar picture. Okay, so that sort of rounds out the cases of these GL2 classical periods. And so moving towards the more general framework of the Relative Langlands program, we're trying to understand this first question, namely how to characterize the set of automorphic representations which are non-vanishing. And we already see that there is some local problems that can arise, namely these epsilon factor questions in the case of Wallis-Bourget. But in higher rank, there are additional features which are not visible in these low rank cases. So I wanted to consider another example just to bring that to the front. And this is actually one of my favorite examples, namely where the so-called Friedberg-Jacquet periods, where here I'm now considering GL2n, so arbitrary rank, and my subgroup that I'm integrating over is GLN cross GLN. So this was studied back in the mid-90s by Friedberg and Jacquet, who proved the following beautiful theorem. If I have a cuspidal automorphic representation, then the automorphic period over this subgroup H is non-zero if and only if my representation is of symplectic type, which in terms of L functions can be stated that this exterior square L function, so this is another automorphic L function associated to the exterior square representation of GL2n. If that representation has a pole at s equals 1, then we say that pi is of symplectic type. And we additionally need a central L value. So this is, again, the standard representation for the dual group, the standard L function. In fact, what they prove is a formula very analogous to what happens in the Hecke setting, that the automorphic period itself is proportional to a product of this form. So there's similarly a local and a global question. So this is the point of bringing this up is, even looking at this formula, it's very similar to the Hecke case. It's this symplectic type assumption that's novel. So one of the nicer ways to think about this is in terms of the Langlands parameters. So we call it symplectic type because it's equivalent to the Langlands parameter actually factoring through the inclusion of the symplectic group embedding into GL2 and C. So GL2 and C is the dual group of G, and a representation is of symplectic type precisely when its Langlands parameter factors through this inclusion. And this brings up an important, relatively modern aspect of the Relative Langlands program, the notion of the dual group of a spherical variety. So I want to explain what that is. And this goes back to work of Sakhlaridis and Venkatesh, who built on work of Prasad and Jacquet in the 90s and early 2000s. But the key insight, which has sort of spurned a lot of work in the last decade, is that the study of these periods is fruitful to actually attack this by considering the harmonic analysis and geometry of this variety X. So I'm taking the homogeneous variety G mod H, so H was my subgroup, but now I'm changing perspectives and studying this G variety X. They tend to focus on special cases, but I'm not going to get into the sort of technical details of spherical varieties and whatnot until maybe a little later. But what do I mean by the harmonic analysis and geometry? Well, the point is that the study of just classical algebraic geometry you want to study a reductive group acting on a homogeneous space. Then using the basic structure theory of such things, Knopp and Schalke explain that, okay, so this is actually much more classical than their work. Using the structure theory, one obtains a root datum associated to the variety. So if you recall from prior talks in this lecture series, the dual group of G is determined by taking the root datum of G and then dualizing it. And what happens when we look at a G variety X is that there is an additional root datum. And so what Knopp and Schalke do is they figure out how to appropriately normalize that root datum so that it can also be dualized to get a complex group, which I'll call G check X. And moreover, that dual group possesses a homomorphism to the dual group of G. So that's saying a lot, but the point here is what Socarides and Venkatesh conjecture, at least in a weak form, is that the non-vanishing of the H period on a representation pi should imply that the Langlands parameter factors through this morphism from this dual group of X. So there's some constraint on the parameters which can possess a non-vanishing H period. What is that constraint? It's that the parameter factors in this way. And the point here is that this dual variety is completely encoded by the geometry of the space X. And this is one of these things where it took me quite a while to become comfortable with, but in the end, it's about as difficult to compute as the root datum of a reductive group. It's just an additional invariant that is associated by this picture. So very briefly, how to think about it. I'm just thinking about the group G as a algebraic group, and let A be a maximal torus in it. Then generically on X, so maybe A fixes a particular pointer, but if we delete certain divisors, then A acts through some quotient torus on the variety X. We'll call that quotient A sub X. Then this root datum that I mentioned on the previous slide is associated to that torus. So the lattice will be the character and co-character lattices for this quotient, and there's a certain set of roots which are determined by the so-called spherical geometry of the variety X. The best way to actually get a sense of these things is to simply compute some. This is actually quite straightforward when the variety is symmetric. It's something that can be computed combinatorially. But in the cases that we've looked at, I'll just give them to you. So in the Friedberg-Jacquet case, the dual group ends up being precisely this symplectic group. So in particular, this statement of Friedberg and Jacquet that the representation has to have this pole for this exterior square L function, which states that the parameter should factor through the symplectic group, is precisely what's being conjectured here by Socarides and Venkatesh. On the other hand, going back to the Wallis-Bourget period, if I take GL2 in this torus, then in this case, the dual group for the variety ends up just being the same thing as the dual group for G. And so that's no constraint at all. That doesn't tell me anything. And even going back to the Friedberg-Jacquet setting, this picture here and this conjecture of Socarides and Venkatesh says nothing about the actual value, this non-vanishing of this central value of the L function. So this global constraint is not contained in this sort of a picture. So all of that to say that while the geometry of the variety gives rise to this dual group, which we can seek to relate to giving a sort of upper bound to the set of automorphic forms with non-vanishing periods, it's not sufficient to characterize. So we need more invariance coming from the variety G mod H in order to say something more precise. And it turns out that one really only needs one more piece of data in good settings. And this is what's called the L function of the variety X. So let's assume, I'm assuming for this slide that my variety is particularly nice. So one thing that I should have mentioned on this slide is that Sacclaridis and Venkatesh make some pretty strong constraints on the homogeneous space G mod H. They so the periods that are actually of interest to a lot of applications, we sometimes maybe aren't able to handle in their language. Nevertheless, everything that I've said does sort of fit quite generally. Any subgroup H, there exists this dual group, and this is the expectation. But strictly speaking, if one of the graduate students were to go look at Sacclaridis and Venkatesh's papers, there would be a lot of adjectives that I'm omitting. In particular, in this case, to define the L function of a variety, we need to make very strong assumptions that are nevertheless satisfied by a lot of cases of interest, namely the Friedberg-Jacquet setting. I mentioned Gann-Gross-Prasad, Galois periods. A lot of these cases satisfy this. So not everything is being included, but this is a good place to start. Okay, so we have several examples where we've seen these central values of L functions, and so the basic question is, can we actually say in advance what the L function should be? Which L function should determine whether or not a period is vanishes for the representation or not? And it turns out that this is essentially a local question. So locally, what one considers is the action of your group on L2 of your variety. So this gives you some large vector space on which G acts. And one is interested in its decomposition. That is the local variant of the period question. And so around 2012, Yannis Sacclaridis, in a sort of amazing calculation, using some pretty deep geometry, combinatorial geometry of these varieties, computes the unramified Plantrel density for this representation. So namely the decomposition of the the G of Z V fixed point. So this is some hyperspecial maximal compact. He decomposes this as a direct integral with an explicit Plantrel density. And what he finds is that the Plantrel density, or the Plantrel measure, has this explicit density with respect to the natural measure on unramified representations. So here pi chi is the unramified representation induced from chi, just via parabolic induction. And the point is that the density itself is precisely an unramified local L factor for a certain representation, which I've called Vx, of the dual group of X. So this, in particular, has built into the harmonic analysis, the local harmonic analysis of your group acting on the variety. It has built into it the knowledge of a particular L function associated to a particular representation, not of the dual group of G, but rather of the dual group of the variety. So So when I look back at this example of Friedberg and Jacquet, one can do this calculation, and in fact, what Soclarides actually computes many of these cases in his 2012 paper. And so there's a very nice table at the end giving the specific L functions that arise for nice varieties. And in this case, if I look at the variety that we're interested in, the local L factor is precisely the square of this central L, or this standard L function, and the value at 1 of this exterior square. And so this is a local computation. And so when taking the product over all places, it turns out that the distinction here will come to a pole. But in any case, this is precisely what we would hope to expect coming from their global results. So this is a rather technical point. Are there any questions at this point? Okay. Let's see. So putting the pieces together, like going back to our goals, we want to give a characterization for the set of automorphic representations where pi is non-vanishing, and we would like to understand the relationship to L functions when it's non-zero. And so this is very far from being known in general, but we have the following pieces of data coming from the harmonic analysis and the geometry of the variety. We have this dual group, this dual homomorphism, and we have this specific representation, V of x of this dual group. And so the conjecture is the following. So let's take pi a cuspidal representation of G, and we'll form this sort of contracted product. So I wish I had my pen so that I could write this, but here G of x acts via the homomorphism phi on the dual group G check, and it also acts via the representation on Vx. And so we take the contracted product. This gives me a variety on which the larger group G check acts. Then the conjecture is that the following are equivalent. The period H is non-vanishing on pi, and the Langlands parameter of pi has fixed points when acting on M check. So that is, if I look at the image of the parameter, I get a subgroup of G check, and then I look at the action of that and ask if it has any fixed points on M check. So this is very sketchy because to make this precise, one needs to deal with several problems. The first is that even if we had the Langlands correspondence, I've said nothing about packets. So I don't know if the issue of L and Arthur packets have come up often in the prior lectures, so I didn't want to get into it. But in particular, it's actually not sufficient to study just one representation on its own in most cases. And so in order to make this a genuine equivalence, one would need to replace just the representation pi with its so-called Arthur-Vogan packet. And the next point that I'll allude to on the next slide is that all of this is essentially making strong use of the assumption I stated earlier that my groups G and H are split. And so in particular, I'm not taking into consideration the Galois action on this variety M check. All right. And that's actually where some of my recent work has come in, is that in cases where the variety X is a so-called symmetric space, by studying sort of rationality questions for the variety X, we're able to actually endow this space M check with a Galois action, so that this fixed point problem can be made more precise. Okay, but in any case, this is sort of the extension of the Langlands picture of parameterizing automorphic representations via these parameters, which encodes the question of H periods, namely this associated G check variety. So let me go ahead and look at the examples that we've kind of carried through the talk to see what these spaces look like. So in the Friedberg-Jacquet setting, we have this representation for the symplectic group that I described earlier. So this exterior square and two copies of the standard representation. And if I take this contracted product, it's a relatively straightforward calculation that this is actually got a nice symplectic structure. Namely, it's just a cotangent bundle for this specific space. So you have this homogeneous space, GL2N mod the symplectic group, and a single copy of the standard representation. And all told, this is precisely the cotangent bundle of that. And if we look at the Walsh-Bourget case, things are a little bit easier. Like I said there previously, the dual group is just GL2 itself, and the representation is this standard. And so when you contract that, you're simply quotienting out by the action of the GL2, and you have the single copy of C2, which we might as well view as the cotangent bundle of C. And just as a brief advertisements for some of my work, which I mentioned on the previous slide, the definition of X here encodes this quadratic extension, this discriminant D, and that's not visible on this line. And the point here is that in a recent preprint, I was studying these periods from a different perspective of rationality of varieties, and I actually recover this representation Vx in a completely different way by just studying the rationality of these varieties. But in particular, the way that they come out in my work, there's a induced action of the Galois group on this variety V check, which is actually compatible in the non-split setting with Galois actions that occur on these dual groups. So in particular, what one obtains is a Galois action on this M check variety, and that's actually what distinguishes between these various forms. There's a different Galois action depending on what the quadratic extension is. And so similarly, for when one wants to consider different forms of this variety, maybe you replace GL with a unitary group, it ends up just being the same variety, but with a different Galois action. But one of the things that I wanted to sort of end on, because this has gotten a lot of attention recently, is that in both of these cases, even though the definition given here it's not at all obvious, both of these spaces are cotangent bundles. So in particular, they're symplectic varieties. They have a symplectic form on them, which is equivariant with respect to the action of the dual group. And so this is part of these recent conjectures of David Bensby, Yanis Saklarides, and Akshay Venkatesh. They conjecture that for any period where we have under appropriate assumptions, the technical term is hyperspherical. The variety that we've described is actually always going to be symplectic, and in particular sits inside an extension of Langlands duality, where here we have a pair, a group G, and a so-called Hamiltonian or symplectic G variety, and that is dual to a pair of the group G check and a Hamiltonian variety for the dual group. So for this talk, how does that fit in? We've been considering the so-called polarized case, where this variety X is replaced by its cotangent bundle. I wanted to mention this at the end because this is something that comes up in a lot of the discussions around these conjectures, though the actual symplectic geometry doesn't necessarily present itself in this talk. But one thing that's very interesting about framing things in terms of this duality, where you allow for more general M, is that it leads to new conjectures. And in order to understand these, you have to allow for a more general notion of period that incorporates things like the theta correspondence. Okay, so things that have been left out of this discussion about the Relative Langlands program is I've made a few comments about working with non-split groups, but there's a lot that's still not understood. I think the best sort of example where something very precise has been stated is Prasad's conjectures on the local distinction for Galois periods, and the similar things in the global setting come up in my work on developing theories of endoscopy and stabilization of relative trace formulas in this setting. But the general picture is not fully understood. One thing that I wanted to say, because it's shown up in previous talks, is that this picture includes the formula of Walsh-Bourget, but it doesn't yet include the theorem of Gross and Zagier, where you replace the central L value with the derivative when an epsilon factor is -1, and the connection to intersection numbers. So higher dimensional generalizations of this exist in the arithmetic GGP and in other settings, and this should be understood in this context, but currently isn't. And finally, something that I find very interesting, but doesn't currently fit into this framework, is that the periods seem to be more general than L functions. There's very natural space groups to write down. I've written down a couple here. The orthogonal period on GLN has been studied by Jacquet and is conjecturally related to metaplectic automorphic forms. And also, if we replace Walsh-Bourget's problem on GL2 with just replacing it to SL2, things become kind of interesting and a little mysterious. And to my knowledge, that's been explored by work of Anand Vardhanan and Prasad, but is still not fully understood. And so there's many cases in this field that we don't understand. And even if we have these very high, general conjectures, there's still much more that needs to be done. All right, so I'll stop there.
So any questions or comments? But this would it be a useful idea to incorporate we now have a categorical equivalence of positive depth things to lower depth things. So uh, you know, can one probably reduce questions to depth zero setting for these distinction problems? I'll have
Um,
to think of, hmm,
so are you thinking
uh,
specifically in the supracuspidal setting or
in general, I think.
in general?
In gen-
Um,
Yeah.
I mean,
So what I mean is that to test if something, some representation is distinguished by something, it should be possible to go to some other groups and replace the representation by a depth zero counterpart.
yeah, I would
Uh,
expect that can be quite useful. I mean, there are some general results in maybe the case of symmetric subgroups uh, where so do these equivalences sit in a functoriality or like is there a way of framing this functorially? Um,
the equivalence is not natural, but you can describe all the choices and describe the space of choices. But if you um, make choices consistently, uh, then this probability should be preserved, I guess.
I mean, I would absolutely believe that if, and in particular, there's work of like Chong Zhang, at least in the context of supracuspidal representations,
Yeah, yeah, yeah. Yes,
where I mean, I guess
yes,
implicitly there is a sort of reduction to the problem in the depth zero case just
right,
by
right. He
sort of
does regular supercuspidals, he studies.
right, right.
Right. So yeah,
Um,
he uses the kind of structure of regular supercuspidals. And yeah, it's basically an inductive thing. It has an inductive structure. But now
yeah,
we can do it for non-supercuspidals, for arbitrary representations.
uh,
So
I see.
this sort of inductive structure. So yeah, I guess this question would be reducible to a simpler setting, but I don't know how to do it for simpler setting.
Uh, I mean, yeah, but I mean, it depends on yeah, even depth zero, you run into the like the corresponding question is not easy in the finite field setting um, necessarily, depending on the. Um, I'm sorry,
Uh-huh.
I'm strictly thinking in the supercuspidal case. So
But in finite field case, it's not possible to describe this distinction completely. I think Lustig has
I
settled
well,
this question.
which well in settings, but I don't know how general.
Yeah, yeah, base change setting.
Phase change, yes, there's been quite a lot of work.
Yes, I think
But
he already finished it in the 90s or something in the base change.
who? Sorry.
Uh, Lustig.
Oh, sure. No, Lustig's result. I mean, he has general results in the general symmetric case. I think like a student of his, Henderson, um,
Uh-huh.
did quite a lot of work, but my impression was that it wasn't complete. Uh, but I could be missing something.
Mhm.
But certainly there are many cases in the depth that is done, which is not known
Yeah,
in
yeah,
the local
depth
field
zero
setting.
already would be a substantial result,
Yes.
and
Yeah.
I think that's also wide open.
Yeah. I think that's probably the state of affairs. Um, and I should also say, like those sorts of methods should apply equally well to cases like orthogonal periods, which for other reasons people typically avoid for the they're somehow viewed as pathological in this world. Um, and this relationship to covering groups is not understood.
Mhm. Yeah, it's one of these like two main branches of representation theory: this problem and the standard functoriality. Or so branching is the basic question in representation theory, and this is the way to address it.
Hmm.
Yes, yeah, it was a great talk.
Oh,
Thank you
you.
so much.
Yeah.
So, any other questions from the audience? If not, let's thank the speaker again. I guess there are not many audience today,
That's okay.
but there may be on YouTube. But we'll, people get to benefit from it over the course of months. They'll see the video.
No,
So, huh?
thanks for letting me talk.
Yes, you're most welcome, and thanks for this wonderful talk. And see you hopefully sometime.
Thank you, Professor Leslie, for the nice talk. Could you share your slides with us? Slides of the talk.
In the chat?
No, not chat. Maybe in the send letter, in email.
Yeah, sure.
Yeah. Okay. Thank you. Maybe you can stop the recording now. Yes.
Yeah.
Okay, maybe if there are no more questions, maybe we can